In this video, we find the formulas for the area of a surface of revolution, and that comes from taking a curve given by r equals r of theta and revolving it either around the polar equivalent of the x-axis or the polar equivalent of the y-axis. The formulas that we're using come from taking those formulas for surface area that we derived when we were talking about parametric equations, and just replacing the t with theta because it's a dummy variable. It doesn't really matter what we call the variable. And then remembering that if we are in polar coordinates, x is given by r times cosine of theta and y is given by r times sine of theta. And I guess there's one more thing that we need to substitute. So we showed in the last video, x prime squared plus y prime squared turns out to be the same as r prime squared plus r squared. So we want to substitute, replace this with this, and we want to replace x with r cosine of theta, replace y with r sine of theta, and then change the axes as well. The x-axis is now the polar axis. So that's the positive x-axis. And we're assuming that y is greater than 0 and x is greater than 0 here. And then instead of revolving around the y-axis, we're going to call that theta equals pi over 2, which is exactly what the positive y-axis is. So putting all of these pieces together, we get our two new surface area integrals. Surface area is the integral from alpha to beta of 2 pi times y, which is r of theta times sine of theta, times the square root of r prime, or r squared plus r prime squared, that'll work, times theta. And remember, this is just the radius, and this is the arc length for that little strip of paper. So I guess we're saying we're over here and we've got some curve. Maybe it looks like this. And this is theta equals alpha, and this is theta equals beta. And we're taking this and we're revolving it around the polar axis this time. So when I do that, in the reflection, that point will end up here, and this point will end up down here, and it's going to be really hard for me to duplicate that curve. Something like that. But the idea is, if I had done a better job with my graphs, we would end up with a surface of revolution. Yeah, my graph's a little bit, it's not very good. It's not a very good graph. But we wrap strips of paper around this, just like we did before in the other sections. And the area of that strip of paper is the circumference, so that distance right there, times this little length, and that is the arc length. And this time, because we're revolving it around the polar axis, that radius is the y value. So the radius is y of theta, which is r of theta times sine of theta. So that's how we get that one. If we took this and we revolved it around the y-axis instead, we would get this formula. But you remember this graph. This is a really horrible graph, but I hope you remember the idea of how this works. Okay, so in practice, I'm just going to evaluate this. Well, that's one version of it. This is if we're revolving around the polar axis. And then we sort of do it the other way around if we're revolving about the line theta equals pi over 2. So in that case, for revolving around what used to be the y-axis, we have x of theta right here, whoops, and x of theta is r of theta times sine of, or cosine of theta. The arc length is still the same. And this is assuming that our curve is in what used to be that first quadrant where x was positive and y was negative, x and y were both positive, excuse me. All right, so we just have to evaluate this integral and this integral, or that integral, depending on what the problem statement says. So let's do a problem. Let's say we have r equals 6 cosine of theta, and we're told that theta ranges from 0 to pi over 2, and we want to revolve around the polar axis. Now this is not the graph in the xy plane, but this is just in the r theta plane. We know cosine looks like this, and at pi over 2, cosine is 0. So when we're in this range from 0 to pi over 2, r will be a positive value except for when it's 0 at pi over 2. So that means everything is satisfied for us to use this equation. We're revolving a curve around the polar axis. So theta is going from 0 to pi over 2, got 2 pi. The radius of that curve is the y values, as given by the y values, because we're revolving. We've got some curve up here. Well, actually, we can actually plot some points. At 0, r is 6. And at pi over 2, r is 0. And actually, I think it's like this. I think that's a semicircle. And we're taking that and we're revolving it about the polar axis. I think we can all see that that's going to be a sphere of radius 3, centered at x equals 0, y equals 3, or that's what it would have been in rectangular coordinates. Okay, so looking at that picture, let me look at the formula for surface area of a sphere. Surface area is 4 pi times r squared. R is 3. So I'm expecting an answer of 36 pi. If we get 36 pi out of this, we know we did it right. Now, you might be tempted to not do this way if you already know the answer is 36 pi. It doesn't always end up being a sphere where we have a known formula for surface area. So let's try it and make sure we understand how to use the formula. But we graph our curve. We sort of wrap our curve with little strips of paper. And we see the radius of each of those strips of paper is the y value. And y is r times sine of theta. And then over here, we're going to substitute in r squared and r squared and then r prime squared with respect to theta. And we'll integrate all this with respect to theta, excuse me. So I'm replacing r with 6 cosine theta. And the derivative of 6 cosine theta is negative 6 sine of theta. That's my r, that's my r, that's my r prime. And then we can just simplify. So it looks like we've got 12 pi out here. And the integral from 0 to pi over 2 of sine of theta times cosine of theta. We can either use a trig identity to simplify that or do a u sub. And then look what happens over here. We've got the square root of 36 times cosine squared plus sine squared, and we all love that. It's equal to 1. That means everything is really simple. So I can take the square root of this 36, which is 6, and I have 6 times 12. So that's 72. Times the integral from 0 to pi over 2 of sine of theta times cosine of theta d theta. Now you've actually got some options here. You can either use a trig identity to rewrite this. Here's the trig identity. Sine of 2 times theta is 2 times sine of theta times cosine of theta. So I could replace this with 1/2 times sine of 2 theta, and then it would be a simple u sub, u is equal to 2 theta. Or I could just do a u sub as it stands. I think I'll just do a u sub as it stands because most students don't remember this identity and they don't think to use it. But if you did think to use it, that would make the integration even easier. Okay, so let's let u be sine of theta. Then du is cosine of theta d theta. And at pi over 2, we get sine of pi over 2, which is 1. At 0, we get sine of 0, which is 0. So this is the integral of 72 pi times the integral from 0 to 1 of u du. So we get 72 pi, add 1 to the exponent, divide by the new exponent, substitute in 0 and 1 and subtract, and you just get 36 pi times 1 minus 0. So we get 36 pi units squared. That's our surface area, which is the same thing we got when we used the surface area of a sphere formula. So that's nice, that works out. It confirms that we've done this correctly. Now again, most of the time, the solid or the surface of revolution is not the exterior of some sphere. So we don't have a formula for that. In the cases where we don't have a formula, we would have to do this. In the cases where we do have a formula, we can use that formula to check our work over here. And that's when we revolve around the polar axis. If we revolve around theta equals pi over 2, then the radius isn't going to be y. In that case, the radius would be x. So I'd have r times cosine of theta here, and otherwise everything would be exactly the same.